Welcome to the first lecture of this series. We're elated to have you join us, and we hope this is going to be a life-changing experience for you, and you're going to be able to go with us through the series. We'll be looking at measurements and units. Measurement is a very important aspect of human life. The 21st century civilization will not be achievable without measurements and measuring tools, because basically our everyday lives depend on them. From checking to know what time of the day it is, to knowing how much time was spent on a task, to knowing the temperature of a space for cooling or heating systems, to counting revolutions of shafts in engines and other mechanisms. In fact, there will be basically no effective medicine, radiology, dentistry, pharmacology whatsoever. Without the ability to measure, we'll have no exact wake-up time, and the concept of lateness will die, because of course people wouldn't have a proper sense of time. Cooking will be random, same as the taste of our food, because there will be no measurements of components we put in our pots. We can't pass information to designers to design things of any kind, be it clothing, machines, whatsoever. Plato once said, if someone separated the art of counting and measuring and weighing from all other arts, what was left of each of the others would be, so to speak, insignificant. Let's start out by answering the question, what is quantity? Quantity is a physical property of a material or a system. Alright? Now, measurement is getting the magnitude or size of a quantity by comparing it with the known quantity of same nature. So from this statement, what measurement actually defines is quantity. Okay, so it's getting to know, attribute a size or a magnitude to a quantity. Alright? So this usually consists of units of measurements, alright, and number of units the object measures. Okay, that's to say, if you want to get the measurement of a quantity, first of all, you have to have a unit of measurement. Okay, so you have to get a unit which you would use as a means to divide the other parts of the quantity. Okay, so let's say you want to know the distance between these 2 points, okay? Between this point and this point. Okay, so what you need to do is you take a certain distance as your unit of measurement. So let's say we take this as our unit of measurement. So we're talking about from there to here as our unit of measurement. Okay, so once we've taken this as our units of measurement, the next step is how many of these units, okay, are in this length. So we now take this length, we divide this whole length by this. That's, we cut out this whole distance into this. So you can find, let's assume what I'm marking are equal distances. So this is us finding the number of our units that measures this object. So let's assume these distances are all equal to this our unit of measurement. So this will tell us we have 1, 2, 3, 4, 5, 6, 7 units. Okay, 7 units. So if we want to name, let's assume we're naming our units meg. Let's name this unit as meg. Now this will be 1 meg, and this distance will be 7 megs. Okay, it's just, I'm using this so you understand the concept of measurement properly. Okay, so this is what the idea of measurement is. Now, after regions began understanding the need for measurement, different regions of the world adopted different means of measuring quantities. But then, for the purpose of uniformity and the removal of confusion when regions will have to interact, the international system of units was adopted to help the world understand the measurements in one set of unit system. Okay, so basically this SI units, which is the fundamental unit, contain 7 units, and these 7 units are every unit you need to measure any quantity whatsoever. Okay, so let's look at them. The first one we have is mass, okay, and the unit down there is in kilogram. All right, and the symbol is kg. We have the next one as length. The unit is meter, and we have the symbol as m. We have time, unit seconds, symbol s. Temperature, Kelvin. The symbol is a capital letter K. Okay, we have amount of substance, which is mole. The unit symbol is mol, mole. We have current, which is the unit is ampere, and we have a capital letter A for the symbol. All right, we have luminous intensity, which has its unit as candela, and the unit symbol as CD. Now let's consider mass. All right, so mass measures the resistance a body offers to the application of force on it. So let's assume a guy is pushing a cart. Okay, now he's pushing the cart in this direction. Once he tries to make this cart move, he's going to notice a resistance which he has to overcome for this cart to move. Okay, now if there is no friction between this and the surface, that opposing resistance that opposes that applied force is the mass of the object. All right, this resistance has no specific direction. It is just felt opposite to the direction of the applied force. So whichever way the guy tries to apply the force, he will feel this resistance. Okay, so basically, as long as there is no friction between the object and the surface in contact with it, then it is the mass he is experiencing. All right, and the mass of a body is measured with the balance. Okay, so we have the beam balance, we have the level balance, we have the chemical balance. So here we have the beam balance in the picture here, and we have the lever balance in the picture here. Okay, so let's move on to length. Length measures the distance between 2 points and can be measured with certain tools like the meter rule or the tape. So we have a picture of them here. If you look, if you can see this clearly, this is a transparent ruler, okay, a transparent meter rule, and it's calibrated. On one side it has centimeter, on the other side it has inches. Okay, so it's calibrated to the cm and inches. On this side we have the tape. Okay, so we can see that above here it's calibrated in inches and below here in centimeters. Okay, so a unit of length, if you take your unit to be centimeter, a unit of length will be from like this point, this long marker here to this long marker is a unit. That's from 2 to 3 is a unit. You can do from 0 to 1, 2 as a unit, but of course it's not very visible here, so you can take 2 to 3 as a unit. 4 to 5 is a unit, that's 1 centimeter. So now how many of this unit is in the full length? That's what we're trying to measure when we measure the length. How many of this single unit is in the full length? All right, so we can get that kind of measurement from the tape or the meter rule. Okay, and the accuracy for this is usually 1 millimeter or 0.1 cm. If you look at the calibration, you will see that the minimum, okay, we can actually read from it is 0.1 centimeter. So we have 10 calibrations before the next digit. So if we start from 5, before we get to 6, we'll have 10 calibrations there. So each one of those ones stands for 0.1. So when you check from 5, you go to 5.1, you go to 5.2, 5.3, down to 5.9, and then you have 5.9 plus 0.1, which gives you 6. So we have the smallest reading we can take from this as 0.1 centimeters. Okay, and okay, that gives us the accuracy of this tool. Okay, so let's move on. We have the vernier caliper. All right, and so the vernier caliper looks just like this. It's used to also measure the length of an object. All right, so basically this jaw here, this claw, is used to measure the outer diameter, while this one is used to measure inner diameter, and this is used to measure depth. The outer diameter is measured like this, okay, then we measure the inner diameter this way, and then the depth this way. Okay, so the accuracy for this instrument is 0.02 millimeters. That's the accuracy, the least measurement we can get from this tool. Okay, so we move on to the micrometer screw gauge. It's also used to measure length, but then it can be used to measure very small lengths. Okay, smaller than what we can measure from the meter rule and the vernier caliper. Okay, this is way smaller, so it has an accuracy of 0.001 centimeter, which means we can take off readings this small from this equipment. So basically, this can be used to measure things like the diameter of a wire, things that are that small. So time measures intervals or duration of events. It can be measured with the help of watches and clocks. The best accuracy we can get from this is usually experienced with the stopwatch, and we can get an accuracy of up to about 0.1 seconds. Let's move on to temperature. Of course, temperature measures the kinetic energy of particles of a substance. Okay, it can also be said to measure the level of hotness or coldness of a body. Okay, and we need to understand that it's the kinetic energy of particles in a substance that generates the heat you experience from that substance, because those particles moving up and down get to collide with themselves, and those collisions get to generate heat. So by reading the temperature, you're actually trying to read the level of random motion or kinetic energy those particles possess. Okay, but then in easy to understand terms, it's the reading of the level of hotness or coldness of a body, and it's usually expressed in scales. We have scales like the degree centigrade, we have the Kelvin, we have Fahrenheit. All right, so mole measures the amount of substance in the bulk sample of matter. We have current that measures the rate of flow of electrons through a conductor. We have luminous intensity, which measures power emitted from a light source. Okay, we'll look at all these other ones in more details as we move on with the course. All right, so we now have this set of units called the derived units. Okay, so these units are derived from the basic units, the fundamental units. Okay, remember I said the fundamental unit is every unit we need to measure whatsoever quantity we want to measure. Okay, so the first one on our list here is the area. Okay, so we know from elementary maths that area is length times breadth. Okay, so if we consider this, we'll see that breadth is a representation of length, which means this is same as saying length times length. Okay, the unit for length is meters, so this is also same as saying meters times meters. Okay, which would give us meters squared. And the unit symbol for area is capital letter A. We have volume, which is length times breadth times height, which are all representations of length. All right, so we have meters times meters times meters, because the unit of length is a meter. So if we multiply all that out, we have meters cubed. So you see, we're using the basic units to derive units for area and volume, which we have just done. Okay, so let's move on to density. So we have density as mass over volume. The basic unit for mass is kilogram. Volume has just been derived to be meters cubed. So we have mass divided by volume, which gives us kilogram per meter cube. Okay, so let's remember that this is kilogram divided by meters cube, but because we're moving the meters cube upward, we have kilogram per meters cube. The cube becomes negative. Okay, so and this is represented by the rho symbol, rho. Okay, so we have velocity, which is displacement over time. All right, and below displacement is a representation of distance. Okay, it's actually distance with direction. So here we have this as a representation of length too. So displacement has the unit meters and time has the unit seconds. They are both fundamental units. So when we divide meters by seconds, we have meters per second. All right, and the symbol is small letter v. We have same for acceleration, which is change in velocity over time. Okay, change in velocity is meters per second, so we have time as second. So if we divide meters per second by second, we're going to be having meters per second square. So if we divide meters per second, we have meters per second, and we divide it by second. All right, so we'll see that this is the same thing as saying meters, all right, per second minus 1, then per second. Okay, so if you look at this, we're going to be having, of course, from indices, this is minus 1, which will give us meters, seconds, raised to the power minus 2, because minus 1 plus minus 1, of course, is minus 2. So you can see how this was derived, meters per second squared. Okay, so for first we have mass acceleration, which is kilogram times what we got previously, meters per second squared, which gives us kilogram meter per second squared, and the unit is newtons. We have this, we do same thing for pressure, force over area, we get kilogram per meter per second squared, and the unit symbol is Pascal. We do that for energy and work, which is force times distance. Okay, and we get kilogram meter squared per second squared, and the unit symbol joules. We do that for power 2, we get kilogram meter squared per second cube. Right, and the unit symbol is watt. Okay, and this SI base unit is gotten from work over time. All right, so we have the last one, which is frequency, and it's number of oscillation over time. Now, number of oscillation is dimensionless because it's just a number of stuff, like it's a count. All right, so all we are left with is the unit for time, which is s raised to the power minus 1. Okay, and then the unit symbol is hertz.